about what she didn't understand and why she thought she might need to. And she said, well, that thing with derivative, I can't remember what it with the chart or something, which is something we're going to talk about next week. I just never really understood that. I was like, that was like 6 weeks ago. Why is this the first time I'm hearing about this right now, that you didn't understand what was going on with this chart? She should have been in, and she admitted that was true. She should have done that. And so very, very important as we get into these things here. As a matter of fact, what we did yesterday and what we're doing today, just going over this homework the last couple of days, is just kind of setting the stage really for the stuff we're going to do as we go forward today. So trace Mitchell, let's trace at 3 here. And while he's doing that, go ahead and trace and zoom in there a little bit. And I want to refresh everybody's memory and really what is happening here. We're talking about finding the slope. That's what the derivative is. And so when we want to do the slope of this curve, we're talking about doing the slope of this tangent line right here. Okay? We want to find the slope of that line. Now the problem is that we only know one point on that line, the point where it touches the curve. So the whole gist of what we were doing yesterday is we were saying that, all right, if I zoom in, if I look at just a little tiny piece of this curve, it looks almost straight. So if I go to a second point on this curve, is that second point on that line? But it's not on the line, right? It's almost on the line, but it's not on the line, but it's darn close. So if I would draw a red line through those 2 points, okay, like so, the slope of that red line, if I calculated the slope between those 2 points, and that would be that red line, that slope is darn close to the slope of the blue line. And if I let those 2 points get really close together, it's really, really close to the slope of that blue line. So the idea is the derivative is the slope of the tangent line. If I want to find the derivative, I can take 2 really close points and get a pretty good approximation. That's about the best we can do right now. Okay? So that's what this is about, what we're doing. So I want to make sure everybody understands that this is a really important formula for us right here. This is the slope between 2 points. We're not going to be using y2 minus y1, x2 minus x1. We want to use function notation. This is the slope formula in function notation. Okay? And this is how we're going to write it. All right? This is slope between 2 points. One of the points is a f of a, and one of the points is b f of b. You guys know when you're excused, football guys? 1? Okay. A f of a and b f of b. All right? Now, so we subtract the y, subtract the x's, that's what this is. All right, now, there's 2 different ideas in this little section. We had a tiny little homework assignment, okay, and they both involve zooming. Now, one is zooming graphically, which we're going to do right now on number 14 that Mitchell's got ready for us. Another way is zooming numerically. Now, they're really essentially the same thing. Okay, zooming here is basically saying find 2 points really close together, estimate the derivative at that point. So let's go ahead and zoom in here, Mitchell. So go ahead and go to your window menu, go to zoom. Okay, let's go over to 3. Oh, we didn't label that point, did we? Let's do that. That's okay, I did. Okay, let's trace at 3, hit enter again. Okay, now let's go to zoom in. Now while he's doing that, and because these guys got to leave here in a little while, part of your assignment for Monday, remember, is that reaction. Now, I might not have been clear yesterday. When you go to the classroom website, I just want to make sure these guys are aware of this before they go. there is an article to read here, right? We're not just reacting to is math necessary, right? There is an article named Is Math Necessary that we're supposed to read. And then write a short, now I said 1 to 2 pages, not half a page is fine, but as you read the article, I think you'll see there are some things in there that might make you really think, and you might want to react to them, and it might be a page long. But that's up to you. Half a paragraph or 2 is probably fine. Do you agree? Do you disagree? What did you find interesting? Create your Google document right here in Classroom, turn it in there. That's due when class starts on Monday, so have that in then. Okay, so back to this. So we've zoomed in, looks pretty straight. Now let's trace there again. Okay, go ahead and trace at 3. And we should have changed our trace step yesterday to 0.01 or 001, whatever, I can't remember what we did. Hit the right arrow, Mitchell. And there is his second point. So what he should be doing is writing down, what you would want to do here is, I'm going to write down that y value as soon as my computer catches up here. Okay, so 0.141021 minus 0.14112, because here's my 2 points. Here's one here and here's one here. And then 3.0001 minus 3. And I want to see that on your paper. So if you've got a problem on the next quiz and it says to zoom in, to find the derivative by zooming, this is what I'm talking about. 2 really close points. Okay? So we go over to the calculator side, we calculate it, we get the slope, and what is it, about negative 0.9 something? Or is it negative 1? 0.999, a few nines, or whatever. Okay? So depending on the point you pick, but that's what it is. Now, this zooming, so when we come back to this, so zooming graphically is doing that. Okay? That's zooming graphically. It's an actual visual representation of going in here and seeing this small window where the curve is straight. That's what it is. Zooming numerically is simply doing the same thing but without doing it with the calculator. So that's number 10. Number 10 said find f prime of 1.5. And I think the function you were using was what? X squared still there? You were supposed to find f prime of 1.5. Well, here's what they wanted. They wanted you to find f of 1.5 and maybe f of 1.5001, whatever, and then do a slope calculation. That's all you were asked to do. That's all you needed to do on 10. It says zoom numerically. Well, what that means is you're just picking 2 close points and doing a slope calculation without the actual physical do the graph, zoom in, that kind of thing. You would know because you'd plug it into that function. Right. So I would say you would write this, right? Now, if you wanted to just get on your calculator, I mean, I like this, I'll be honest. I like you to get the habit of writing out your function notation because, number one, that communicates to me what it is you're using, what you're plugging in. But if you wanted to just go 1.5 squared and get that value, 1.501 squared, get that value, and then write those values down, y minus y over x minus x, I'm okay with that too, as long as you show this slope calculation in one shape or another, okay? But that's all zooming in. So really that's what this whole section was about, is 2 points really close together is how we at least approximate the slope. Yes?
So for both of them, we still use those 2 points, we just don't look at it on the calculator.
It's just not on the calculator. So when it says zoom graphically, now, how would I even know? Probably, I'll be honest, on the next quiz, I'm probably not going to have you do it on the calculator. I'm not going to have you zoom in, zoom in, zoom in, right? Because I don't even know how. I guess the only way I would know is have you go to your window like we did on that one problem, go to your window and write down what your window is. But I don't care about that much. why we did it in these problems is for learning the concept, right? So when you're doing this, zooming numerically, where you're just picking two close points and just plugging them in and doing the calculation, my hope is in your head, you're picturing what's happening. You know, in your head, I hope you have this picture in mind when you pick two really close points, right? So you're getting the concept of what you're doing. You're just not memorizing a calculation. That's not what I want. Okay? Now, the other part of this is the last part then, would be the number 27. In number 27, you were supposed to take that graph. Now, this is not the right graph. But you were supposed to take that graph on number 27, and you were supposed to just sketch little tangent lines. Probably from previous classes, people had already done that in there. Just take your pencil, sketch little tangent lines, and estimate what the slope was. Now, according to my answer book, let's go through those. So at -1, what'd you get for f prime? For 27? Well, I've got 2. Now, 1.5, I heard 3/2. Okay. Is everybody at the right place here? So it's got to be positive, doesn't it? So at -1, all right, so we're looking at the slope right up here. So you would want to, so at -1, we would go in and we would kind of sketch a tangent line right here. Oh, that's at 1/2. Oh, I got it right here. Never mind. I got it right here. There you go. Oh, well, that's probably what, see, some of you guys might have done the same thing I just did. Yeah, no wonder, because that is negative, isn't it? Yeah, some of you got to look at the units, don't you? So there you go. So -1. So -1 attaches there. Now what I typically do, my only hint on doing these problems is to make these lines nice and long. On our next quiz, there will be a problem like this, for sure. Here's a graph, estimate the slope at a certain point. You don't even know what the equation is, so you can't plug in 2 points, right? You can't plug in 2 points and do a slope calculation when there's no equation to plug into. So all you can do is do this. So what I typically like to do is do a run of 1. Now here a run is 2 boxes, or 1 is 2 boxes. If you do rise over run and your run is 1, it makes it easy. So you go over 1, it looks to me like we would go up, oh shoot, you know, it's about 1.5, 2.5, it's about 3.5 of these boxes, okay, but each box is 1/2, right? So what is that? That's a little over 2, right? A little over 2. No, 3.5, that'd be a little under 2. Right, a little under 2, 1.75 or 2. They put 2 in there. So if you're in that ballpark, right around 2, a little less than 2, a little over 2, that'll be okay. I'll look at your line, I'll look at your little slope triangle and see what you have. Okay, probably should have went back 1 and down and went from there. Okay, all right. What about at, what's the next one we have? At 0. What'd you have at 0? My book has -2. Again, give or take. At 2, definitely 0. That one's easy. That's down here, right? That's down there. And then the last one, or at 4, I guess. No, I'm looking at the wrong one. 3. 2, about 2, something like that. Okay, but again, that's the idea. So at this point, we really have 2 ways of figuring out the slope at a point. We can, if we know the equation, we can pick 2 really close points and do a slope calculation, or we can take and sketch a tangent line and estimate it that way. All right. So let's go ahead and talk about the next section here, and there's not a lot, going to be a whole lot to get to today. We're going to do a calculator activity here in a little bit. Mitchell, thank you for doing that. Courtney, you get logged in? I did. It'd have been nicer if you reminded me. Yeah, hers, it won't even show room 414 as a network. Well, that's what I'm afraid of. In 2 weeks. Okay, here's what. Okay, actually, I don't need this on right now. Okay, so everybody else got their documents, I hope. Oh no, it's you got a minute. You got a minute. All right. Okay. Yeah. Don't. Well, I guess the hats are off. That's fine. Whoops. Okay, now if you get a message about me sending you that document, don't override it. You're getting it again. But I'm just trying to get it to go to Courtney's here. All right, you guys need. All right, so there's that paper, right? There's that paper reaction. Next line.
Oh, now I know.
And then this is that document that I sent you called first derivative test. You follow these directions. This worksheet goes along with that. So you fill out this worksheet based on. Good luck today, guys. Thank you. All right. All right, so everybody take the hats off. Yep, take the hats off.
Ooh,
What?
$300.
No, I think.
I'll go get him.
Chris took his off.
Oh, they just took the calculator with the hats
I think Brock and Cody did.
How far do these things reach?
Yeah, not that far. So.
See the brick wall?
Okay, has everybody got the hats off? Oh, okay. Now that was Courtney. That was my fault. That part. That one. Okay, so we got those. All right. Aha, here we go. You're in.
Would you do Lacey and Nelson for Charles?
What?
I don't think.
I would settle for a
All right, here we go.
We put these
Uh,
back now.
Actually, we don't need to. We won't need to. Let's see. All right. Now, get your notes out. Get your notes out. And there's a couple things here you may want to jot down as we go along. Now, it's up to you. Now, at some point along the way here, and I think writing it down is helpful because one of the things that we're going to find over the course of the next several days is there's a lot of stuff going on here and connections and things we're talking about, and it's easy to get confused. Now, we're going to work over the next several days to organize that information, organize our thoughts, and put it all together and make it easier to study and be ready for our next quiz. But section 6 and 7 basically take what we've learned. Think about this now. Section 4 was just, here's what a derivative is. Slope, rate of change, we talked about those things. Section 5 was about how can we calculate a slope. Then that's that zooming in thing. Pick 2 points really close together, draw a tangent line and do rise and run, that kind of thing. What 6 and 7 are about is finding all these connections. This graph right here, and you guys have this, but you don't need to pull it up on your calculator right now, it's fine. This graph here is the F graph, and this one down here is the F prime graph, and we've already talked and hinted about some of the kind of connections between these graphs, but now we want to kind of formalize that over the next several days about what is happening and what are the connections between F and its derivative. Okay? So as we go through these, you might jot down a couple of whatever. It's going to be somewhat unorganized here in the beginning, but then we get to Monday and so forth. We're going to work really hard at organizing all of this stuff. So if I drag this point, let me go down here and do it. If I drag this point right here, and I get on the blue graph. So now remember, the blue graph is F prime. Remember how we talked about the F prime, the Y values are the slopes of the red graph. Okay, what can you tell me about the blue graph right through here? The blue graph. It is decreasing, but the blue graph's also decreasing down here, and I'm not talking about that. So I'm talking about something else. It's positive, right. Its Y values right through here, the Y values on the blue graph are positive. Now, right through here, what's the red graph? Not positive. Yeah, because down here it's negative. It's going up. It's increasing. So the term we would use is increasing. So that might be worth writing down right there. When F prime is positive, right through here, F prime is positive. We're talking about its Y values now. F, the red graph, seems to be going up. Now, as you're writing that, I'm going to move the point over here farther because the blue graph is also positive over here. And is that same thing true? Over here, the blue graph is positive. The red graph is going up. I agree. And then likewise, right down through here, what's the blue graph? Negative, and what's the red graph doing? Going down. So, and that makes sense because slope, derivative is slope. So when the slope is negative, the graph should be going down. When the slope is positive, the graph should be going up. So that makes sense. But there's more to it than that. Let's talk about what you were just saying as far as going down. You were telling me right through here, the blue graph's going down all the way to here. Let's go back and forth here. The blue graph is going down this whole time. What's the red graph during this time? What could you say about the red graph? What's one thing that would describe everything about the red graph right through here? Concave down. Isn't that true? During this whole time, the red graph is concave down right till there. So, what does that say? When F prime is going down, F is concave down. Seems to be the case. And likewise, we go to the other side when the blue graph, when f prime is going up. The red graph seems to be concave up. Okay, those seems to be some interactions we have there between f and f prime. Now we'll talk more on Monday about what that means. What's it mean for the slope to be going down? What's that mean? That's different than the slope being negative. Those are two different things. The slope decreasing is different than the slope being negative. So we'll talk about that. All right, let's talk about some other interesting things, like right here. At this point right here on f prime, what do we call that? Well, no. On f prime, what do we call it? That's a root. So right here we have a root on f prime. What do we have on f? A local max. That's interesting. A root. Of course, we know that when we talked about speed and rate of change, this would be like the velocity. Well, when the velocity is 0, the car is turning around, sure enough. Think about slope. When the slope is 0, oh yeah, look at the slope right there. 0, we got a local max. Now what about this other root? That is a local min. One of the things we're going to talk about today, the activity we're going to do, okay, now I'm getting there. Okay, let's grab this one. There we go. When we go over to this root, we have a local min. So one of the things we're going to talk about today is if the derivative is 0, how do we tell if it's a local max or it's a local min and what's going on? And that's one of the things we're going to talk about today. All right, one other point of interest would be this point right down here. We have a local min right down here on f prime. When the blue graph has a local min down here, what do we got on the red graph? We got an inflection point. So there's a real connection here between the things that are happening with the f prime graph and what's happening with the f graph. And all the important points and characteristics about up and down and concave up, concave down, inflection point, local max, local min, there seems to be a connection here between f and f prime on when those happen. And what we want to know, what we want to be able to do is just know those cold. We just want to know when this happens on one, then this is going to happen on the other, and vice versa. And that's one of the things we're going to work real hard on the next couple days. Okay? All right. So there's a couple of definitions that we need to talk about here today. First one is a stationary point. A couple of terms that we need. If you look in your book on, I think it's page 55, there's all kinds, 55, 56, there's all kinds of bold-faced words. Now, a lot of them we've already know. Local max, local min, concave up, concave down, inflection point, that kind of stuff. Okay? So the first thing we want to define today is a stationary point. X sub 0 is and I'll abbreviate here, stationary point of f of x if f prime of x sub 0 equals 0. So the stationary point is the x coordinate that makes f prime have a y of 0. Now that kind of makes sense because f prime, stationary, kind of makes you think of not moving, being stationary, and f prime we've used as velocity, and when the velocity is 0, the car is certainly not moving. It is stationary, like at a turnaround point, like at a local max or local min. And that's what we had talked about. Okay? So that seems to make sense. That's going to be a very important point for us to talk about. We'll solve a lot of equations using this right here. We will do the derivative, and we will set it equal to 0, and we will solve that equation because we want to know where the derivative is 0. That is a key point for us. Well, think about it. If it's a max, if we're doing a profit equation, we might be really interested in the max profit. Or if it's the snowmobiler stranded trying to get to the gas station, we might really be interested in the minimum time. Well, what happens at a max and a min? One thing that happens is the derivative is zero, right? When does the ball get to its highest point in the metrodome in that problem? We did it when the velocity was zero. That's like doing when the derivative is zero. All right, here's another term for you. Critical point. Critical point. X sub 0 is a critical point of f of x if f prime of x sub 0 equals 0 or f prime of x sub 0 is undefined. It's kind of a square rectangle kind of thing, right? Are all stationary points critical points? Yes. Are all critical points stationary points? No, right? So stationary point is like a subset of critical point. Now, we will talk about stationary points most of the time, early on especially, because we're not going to worry too much about functions where f prime is undefined. Most of the functions we do are going to be nice and smooth, nothing weird going on, and so the derivative won't ever be undefined. But sometimes it is. Now, yesterday we talked about two situations where f prime was undefined. What were they? Sharp point, like this, or maybe like that. Some sort of a situation like so. The derivative is undefined. What was the other time? So x cubed, or excuse me, cube root of x. You might get a vertical tangent line. Now, this would be a local minimum. This is still a local minimum. So we talked about local max and mins being when the derivative is 0 and the slope is 0. Local max and mins could be when the derivative is undefined. So if we want to find a max point, we probably not only have to check where the derivative is 0, but maybe where the derivative is undefined, because we could have a max point. Now in this case here, that would not be a max point, but it'll be a place to check. So that's one of the things we'll be getting into, one of the things we'll talk about. Okay, let's go back to this idea of stationary point. There are three different possibilities for the derivative to be 0. Now the two we've already seen are pretty obvious ones. A local max, right? Derivative is 0. A local min, right? Derivative is 0. But you can get a graph like this. X cubed is a great example. Right there, the derivative is 0. That is a horizontal tangent line. Okay? Is that a local max or min? No, we call that, we're just going to call it a flat spot. We have no fancy name for it. We're just going to call that a flat spot. It flattens out, but it is not a local max or a local min. It's neither one. It's an inflection point, but it's also a stationary point because the derivative is 0. Now, not all inflection points are stationary points, right? I mean, like on sine graph, you have an inflection point, but the derivative is not 0. But there happens to be one. Okay, that's actually the calculator thing we're going to do here just very shortly is dealing with this. Okay, I want to make sure I've talked about everything else. Okay, one last thing. We have local max and mins, okay, which is this, or maybe a sharp point, or maybe something like that, right? So they could be curved, they could be V's, that kind of thing. That's a local max or min. Now another term for that is relative max or min. Now you don't see that very often. That's kind of an older term, but it does pop up once in a while in some of our AP test review things and some of those things we do, some worksheets I pull out sometimes, they use that term. We also have what's called a global max and min. Now, this is a little different. A global max min is the highest / lowest point on the interval. Now, if there's no interval, if it's negative infinity to infinity, you might not have a global max or min. Like on x cubed, it just goes forever up and forever down, and there is no global max or min. But if you've got a fixed interval, a closed interval, then you should have a global max min. We'll talk a lot more about this. I just want you to be comfortable and familiar with the term. So, for example, I could have a graph that goes up, down, and up. Well, in this case, my global max min is also my local max and min. Right? Another term that's sometimes used is absolute. Let me put that here. Sometimes this is called absolute max and min. Global is sometimes called absolute. Well, here my global max and mins would also be my local max and min. However, if I extended this a little bit down to here and extended this up to here a little bit, now I would have still my local max and mins would be there, but my global min would be down here and my global max would be up here because those are the highest points. So they can be at endpoints. Global max and mins can be at endpoints. Local max and mins wouldn't be. Local max and mins are always going to be peaks and valleys. And we don't call an endpoint a local max or min because we can't really see what's going on the other side. Okay, so that's pretty much where I want to stop on section 1.6. There's just so much stuff that I just don't want to just try to get through all of it. I want to let you have a chance to absorb some of this and work on some of these things. So, we've got that paper, that reaction thing to do for Monday. What I want you to work on right now is this worksheet here. Now this worksheet goes along with that document that I sent you earlier. So on your calculator, pull up that first derivative test document. It's called First Derivative Test. First derivative test. Now, what the first derivative test is all about is testing a function to see if you have a local max, a local min, or neither, like what I show on the board here. So we already looked and we said, hey, a local max or min is going to be, could be when the derivative is 0, or maybe when it's undefined. How do we tell, if we know the derivative is 0, how do we tell if that's a local max, a local min, or a flat spot? Well, the way we do that is we test it using this thing called the first derivative test. And that's what you're going to discover as you go through this worksheet. So you open up that document that says first derivative test, you follow the directions on the worksheet, you answer the questions, you fill in the table, and then we'll talk about it on Monday. So I want you to work on that right now. If you get done with that before time's up, then you can start working on the 1.6 day 1 homework questions, which again, it's relatively short, kind of like today's one. Okay? So you have all kinds of time to trick or treat. Okay? Nobody will have to stay home from trick or treating because they had to work on their calculus. You're welcome. All right, so that's what you got. The rest of the time is yours to work.